So, you know all of this about the inverse. And you get to this point, and you're looking at this, you know all that different information. Let's write the equation for the inverse. For the 2 to the x. Let's just do the 2 to the x one. I'm going to need to erase that, because I'm going to need that space. And we're going to do the equation for the 2 to the x. So y equals 2 to the x, dotted line, we're going to switch the x and the y. And then I'm going to let you make it y equals. I'll let you do the math to make it y equals. Yeah. I'll let you do that math. No, you're going to have to try to work it out. Yeah, you do the math. You work it out to y equals. I see erasers working some. I see people scratching stuff out. I see someone has either given up or worked it. Which is it? What'd you do? All right, you got to be real careful because the y is up here. It's not 2 times y. What you just did would work if it was what? 2 times y. Is that okay? Yeah. Remember, the y is up there in the exponent spot. Oh, I see a lot of people racing after we did that. Yeah, because if the y were down here beside the 2 times y, it would work. But it's what? 2 raised to the y. Y. Oh, we see people trying to take the y root of stuff. Well, kind of running into a brick wall back there. Yeah. Over here against the wall, what are we doing? Just not get. Okay, good. There is no algebraic way to do it. There's no algebraic way to find the inverse. Can't be done this way. It's not algebraically possible to do it. I mean, if you look over here and you go, Mr. Evans, yeah, you can. You just subtract 1. It would work for this one, and it worked for this one, but does it work for that one? Oh, just divide by 2. Works for this one, works for this one, but it wouldn't work for this one, would it? What happens is you run into a wall because there's not an algebraic way to do it. You're supposed to run into that wall. Now, here's the scary part. We know the numbers. We know what the inverse should do. We know the graph, but we don't have an algebraic way of doing it. This is when we have to think, okay, we know how it looks on a graph. We know the solutions. If we could work it, we already got a list of solutions, right? So we have to come up with it. And what math folks did is they came up with called transcendental functions. And what a transcendental function is, it transcends. Does anyone have anything to say about the word transcends? You better have something to say about it. What do you think of when you think of transcends? I tell you, transcends. What's that word? Like go above something. Goes above it. Okay. Transcend goes above it. Have y'all ever heard of something in English or history closely related to that word transcendental? Yes, sir. Transcendentalism. The man's playing the game. He's going to learn something. Do you know what the transcendentalists said? Anyone want to take a guess? Yeah, any guess? Okay. Transcend. Transcendentalists were big into nature, and this is probably overly simplified, but here's basically how it works. Throw the pen up in the air. The pen falls back down. I throw one of you out the window. You fall, right? What are you seeing an example of when I throw the pen up in the air?
Gravity.
Gravity. So if you look at nature long enough, here's all the nature part. We got all the numbers. We know this is true. But in your brain, you come up with the concept of gravity. Do you ever really see the gravity? No, you don't ever see the gravity, but from nature and what you've seen, you know there's this thing called gravity. Well, what transcendental functions do is they go, okay, we know there's these inverse functions. We know the values of them, but they're not algebraic. So we're going to have to give them a name that fits what they do. And that's a transcendental function. So what happens is this one we call y equals log base 2 of x. This one we call y equals log base 5 of x. And then this one we call y equals log base 10 of x. And those are transcendental functions that we know make the inverse happen. Can we really do it with algebra? No. Somebody says, well, did you just make them up? No. We didn't just make up gravity, right? I mean, we saw the results and we named it. Yeah, we saw the results and we gave it a name. We didn't, we didn't just make up something that wouldn't fit into the system. It fits the system of math because we already know what the math is. We couldn't do it algebraically. These are called transcendental functions. I'll go ahead and tell y'all. When y'all were in geometry and y'all did sine and cosine and tangent, those are transcendental functions. They're designed to do what we want them to do. Okay? We knew the numbers worked, but we didn't want to have to keep doing it the long way, so we abbreviated it. Sine, cosine, tangent. Those are transcendental functions. And logarithm is a transcendental function. So, do you now know why when you talk about logarithms, you talk about logarithms of different bases? Yeah, because the base tells you what? What does the base tell you? It tells you which what? Come on. What is the base telling you? It's telling you it's the inverse of which what? Okay, base 2, log base 2 is the inverse of the exponential function what? 2 to the x. Log base 5 is the inverse function of what? Log base 10, the one y'all use in chemistry all the time, is the inverse of what? 10 to the x. This one's the inverse for your scientific notation stuff. See? 10 to the x. So if I see y equals log base 3 of x, what do I know the exponential function was? 3 to the x. Yeah, 3 to the x. See? So when I see the log, that base is telling me which one of these exponential functions it is the inverse of. And that comes in real handy because then you can understand logs a little better. What I'm doing is telling you why logarithms exist and why these little numbers are important. Okay? Now, well, that's why Euler had to go to the mountains, because we couldn't do this with algebra. And he actually went to a specific mountain. He went to the Transcendental mountain. Now, he went up the mountain, and the laws were given to him on a platinum sheet. It's a platinum sheet, and I don't know exactly how it worked, but while he was on the mountain, one of the math deities began to tell him the laws. And he said, these are the laws. And these laws are what you need to make these inverse functions work. So these are the laws for those inverse functions. Now, we call them the logarithm laws. Hope I spelled that right. I'm on video. The logarithm laws. The logarithm laws. And here there's really just 7. Some people think there's 8, but the 8th law is not what he brought off the mountain. He only brought 7 off the mountain. I could start doing some kind of weird stuff about perfect numbers and go, yeah, he had to bring 7 because it was that perfect number that y'all hear about and all that, which I don't know anything about that. 7 laws off the mountain. Here is law number 1, written on platinum. They had it in the Louvre in Paris for a while on display. And then when they were making that movie at the Louvre about the Mona Lisa, they lost it. Because they had it somewhere in that movie, and then they lost it, and it's somewhere, they hadn't been able to find it in the Louvre. But it's a tablet about this big, and it's got the 7 laws written on it. It's platinum, like 99% pure platinum. All right, law number 1. Log base b, any number down there at all, of 1 will always give you 0. Well, look at it. Log base 2 of 1 is 0. Log base 5 of 1 is 0. And log base 10 of 1 is 0. And then remember, if you have y equals b to the x, I'll write a little bit over here, y equals b to the x, if you put 0 in there, you're always going to get what out? 1. So the inverse, y equals log base b of x, has to turn 1 back into what? 0. There's a little explanation of how the law works, and you can see it if you see the numbers. And what gets y'all in trouble is you won't use the laws. You want to go back and try to use some algebra. Use the laws. And I know what makes it difficult in your science classes is your professors in college that are teaching you chemistry, they've done the laws for so long, they're skipping laws. They're skipping laws, and they're just skipping a couple steps, and you have to go back, you have to go, okay, you use law 1, you use law 4, or you use law 3. And that's what I do when I tutor kids in chemistry. I can't do chemistry. I can't write the original equations, but I can show them the rules that he was using to get to each step to the answer. Because I trust them. That's rule 1. It doesn't matter what base is down here, what are you going to get? 0. Rule 2. Rule 2 says if you have log base b of the same value, you will always get 1. Well, in other words, log base 2 of 2 gives you what? 1. Log base 5 of 5 gives you 1. And log base 10 of 10 does give you 1. Well, it doesn't matter what that base is. If you put a 1 there, you're going to get that base, right? Is that okay? So if you put the base here, it's got to turn it back into 1. I didn't do any algebra, I just know it has to do that. All right, rule 3. And rule 3 will take me writing a little bit here, but rule 3 says that if I have log of a base, and I had the same number here, raised to a power, it will always reduce down to that power. Okay, this is the one they use in your chemistry class, and all of a sudden the logs just disappear. Okay? I'm going to show you how that works. I'm going to erase right here and show you how it works. I'm going to do it with log base 10 because this is what your chemistry teacher does to you. Log base 10 of 1,000. We know that log base 10 of 1,000 equals how much? 3. Is that okay? We know it's supposed to equal what? 3. Everybody okay with that? Well, here's what happens. What your chemistry teacher's doing in their head is they're doing that. That's 10 to the what? Third. And I've just told you if you have log base b of b raised to a power, it just equals that power. Okay. Is that all right? Now, here's why it comes in handy. Oh, I just erased that one. I shouldn't have. Let's think about this. Log base 7 of 49. Somebody says, but Mr. Evans, we didn't do any log base 7s. You're right. We didn't do any what? 7s to the x. But does everybody agree that 49 is 7 squared? Equals 2. Okay. So once you start learning the laws, you can apply them to all different kind of bases. And that's that rule. That's rule number 3. All right, rule number 4 is very handy for rewriting problems. And it says if you have log base b of some number that's not the same as the base raised to a power, you can just bring the power to the front and multiply it by log base b of that number. And that's rule number 4. Now, when you go to your chemistry class from Miss Comerford, if you will take this list with you, what she's trying to do now is when she's doing the chemistry, she will, and she skips a couple steps and you raise your hand, she's going to try to tell you which law it is. You know, she's going to go, okay, look at law 5. But they use them so much that they know they work and they know the law's there, but they don't know which law it is, and they probably can't write out the law in this form, but they're just going through it and they know it. All right? What this means is if I had log base 7 of 3 to the 5th, I can just simply put the 5 in front and write it like that. Okay? That's all it means. Or I could take, if I had this, I could turn it back into what? That. Is that okay? I can show you it works if we do one where they are the same. Let's do log base 2 of 32. We know that equals 5. Does everybody agree that equals 5? Okay? Well, look at this. If I do log base 2 of 2 to the 5th, rule number 3 tells me that has to equal what? 5. So if I agree that rule 3 over there tells me that equals 5. Well, if I did rule 4, I would get 5 log base 2 of 2. Well, what does log base 2 of 2 equal? Log base equals what? 1, right? Is everybody okay at log base 2 of 2 equals 1? And 1 times 5 would equal? 1 times 5 would equal 5. So you still get 5. So all three of those rules all give you 5. So it's kind of neat. Rule 2, 3, and 4, you can use them here in different ways, and you still going to get the right answer. Still get 5. All right. Then, after that came Rule 5. And Rule 5 is used in science again. Here's Rule 5. Rule 5 says that if you have a base raised to the log of that same number of some value here, it will work out to be that value. Okay? You don't have to work it. You know it's going to be that. We'll try to make that happen to show you that it works. All right? Go. I have 7 raised to the log base 7 of 49. That rule is telling me I should get 49 out when I'm done. Right? Everybody agree that rule is telling me I should get what? 49. Well, let me show you that it really works. Everybody agree that 49 is what? 7 squared. We know that equals 2 because of this what? Rule. And so we get 7 squared, and 7 squared equals how much? 49. Okay? Now, this is the rule that your chemistry teacher is using when all of a sudden all the logs disappear. She'll have something written like this. She'll have log base 10 of 3x equals 5. She'll put a 10 down here so that she gets 10 raised to log base 10. But if she puts a 10 there, what does she have to do over here? 10. And then all of a sudden she writes 3x equals what? 10 to the 5th. But she never puts a 10 here and a 10 here for you. She just writes this. Okay? But that's the law she just used. She put a 10 here so she'd have 10 raised to this, so that it would leave just what? 3x. But if she puts a 10 here and raises it to that, she's got to do the same thing to the other side. She's got to do what? 10 to the 5th. And this is one of those cases where they use this all the time, and you're sitting there going, where'd the law go? Where'd the law go? Okay. Now, Rule 6 is an easy one. If you'll just believe it works. You have log base b of m plus log base b of n, and that equals log base b of m times n. That's so that you can combine two logs with the same base together. And if you want to know why you'd want to do that, have you noticed that our first 5 rules only deal with one log? You can't have 2. But now this is a rule that will give it to where if we have 2 logs of the same base, we can combine them together. Y'all do it more to combine them together. To be honest, when I was in school, we used it to separate them apart so we could use the charts. But y'all are going to use it to combine them. And so if it's log base b of, okay, I had log base 2 of 8 plus log base 2 of 4. That's going to equal log base 2 of 4. What's 4 times 8? 32. So that should be a 5. Does everybody agree that should be a 5? Log base 2 of 32 is what? 5. Well, if you do this, if you do log base 2 of 8, that equals 3. Okay? And what does log base 2 of 4 equal? It equals what? 2. So you do get what? 5 equals 5. I used the rule, I made 8 what? 2 to the 3rd, and I made 4 what? 2 to the 2nd, and then I used one of my rules over there. I did it this way without using this rule, And then I did it over here using the rule. It works. Rule number 7 is the same as that rule, except that's a minus sign right there. Rule 7. Log base b of m minus log base b of n equals log base b of m over n. And those are your 7 rules. Now, and I'm going to give you rule 8. He did not write rule 8. He did not bring rule 8 off the mountain. Okay? He did not bring rule 8 off the mountain. But I'm going to add rule 8 in there. This is something his disciples wrote. They added this to the story. And basically what they did is they combined a couple of these rules to make a rule that makes life easier. All right? Rule 8. And like I say, this one needs a little star back. This is not really one of his rules. But rule 8. So I can probably pick it right here. Okay. Do it in different colors so they know it's not. Okay. Okay, this is called the change of base rule. And what it said was,